Hello everyone. In this video we look at the special case of an oblique projectile, which is the projectile on an inclined plane. Now when we look at say for example an object which is projected with a speed u from an inclined plane which is making an angle alpha with the horizontal. So the inclined plane is actually making an alpha with the horizontal, and the angle of projection is theta with respect to the inclined plane. So here the angle made by the projectile with the inclined plane is theta. Now the way we will go about studying this projectile on the inclined plane, now it is possible that we may throw the particle like this, or it can be thrown even the other way. Now we'll see that in one case the particle is going to be decelerated as it goes along the plane, which is what the example we took here, and in another case it is going to be accelerated along the plane, so which will be if you throw the particle the other way. So we'll just take a look at what this is. So the way we'll go about studying this projectile on inclined plane is, we will consider the reference x-axis to be the direction of the plane. Now the way we'll look at the horizontal over there in case of the normal oblique projectile, same way here we will be treating the direction along the plane, which means the direction normal to the plane will be the y-axis. So along the plane we will take it as the x-axis, normal to the plane we will take it as the y-axis. Now the initial velocity which will be having two components. One will be the component along the plane, which will be u cos theta, and the component perpendicular to the plane will be u sin theta. Similarly we know that in case of the oblique projectile, the acceleration of the projectile is vertically downwards g, but here since the directions we are taking are along the plane and normal to the plane, we will have to resolve the g. So g will be vertically downwards, and if alpha is the angle made by the inclined plane with horizontal, we see that the angle between the vertical and normal to the plane also will be alpha. So here we can look at it by using the properties of the triangle. So if this is alpha, then think about it, we draw a vertical and this is the normal. So this is alpha, means this will be 90 minus alpha, and this is going to be alpha because the total angle will be 90. So the angle made by the normal with the plane will be 90. So if you resolve the g into the components, the perpendicular component, which means the component of the g which is perpendicular to the plane, will be g into cos alpha. Here alpha is the angle made by the inclined plane with the horizontal, and remember theta here will be the angle made by the projectile with the inclined plane, and the parallel component of this acceleration. So if one component is g cos alpha, the component which will be along the plane will be g sin alpha. But since we are taking the right side, or rather we are taking along the plane this way to be positive, the opposite direction will be negative. So as per our sign convention, we will be taking it as minus g sin alpha. So if we are going to use the equations of motion along the plane and perpendicular to the plane, then while substituting the value of the acceleration, so we will be taking it as minus g sin alpha, since it is in the opposite direction to the initial velocity. So initial velocity is u cos theta, which is parallel, it will be in this direction. The acceleration is exactly in the opposite direction, so hence we are taking it as a negative by following our sign convention. Now as we see, the particle will be getting decelerated as it moves from O to P. So P is the final point where it is touching the surface of the inclined plane again, and just to keep it in perspective, OP will be the range of the projectile. OP will be the range of the projectile. Now the way we'll go about getting the derivations or results in case of the inclined plane is just following the analogous results that we have in case of the oblique projectile. Now starting from the time of flight. In case of an oblique projectile, the time of flight formula will be 2u sin theta by g. So in case of the oblique projectile, u sin theta is nothing but the perpendicular component of the velocity, initial velocity, and g is nothing but the perpendicular component of the acceleration. So the analogous formula over here for the time of flight will be 2 u perpendicular, the initial perpendicular component of the velocity, divided by a perpendicular, the perpendicular component of the acceleration. So we have the result, which is the u perpendicular will be u sin theta, and a perpendicular will be g cos alpha. So already we have these two results being discussed. So the time of flight for a particle on the inclined plane will be 2u sin theta by g cos alpha. So all that we are trying to do is just look at the analogous result or a similar result in case of the oblique projectile, and replacing the corresponding terms with either the parallel or the perpendicular component of initial velocities or the accelerations. Now we'll go to the other result, which is about the maximum height. So in case of the oblique projectile, maximum height formula will be u square sin square theta by 2g. So if you look at this, this is nothing but the initial velocity of the projectile in the perpendicular direction square divided by 2 times of the perpendicular acceleration. Now here in case of the particle which is projected along the inclined plane, we see that the maximum height h will be equal to, here also the perpendicular component of the velocity initially will be u sin theta, and perpendicular component of the acceleration will be g cos alpha. So the value will be u square sin square theta by 2 into g cos alpha. This will be the maximum height. Now looking at the horizontal range, as we were just talking a little bit before, the projectile while it is moving along the plane, it is getting decelerated, and the value of deceleration will be minus g sin alpha. Now what we'll do is we'll try and look at the 1D motion equation, s is equal to ut plus half at square. The only thing is we will have to use the analogous terms, which means here this will be the distance covered along the plane. If we take the u to be the parallel component of the initial velocity and a to be the parallel component of the acceleration. So if you look at these values, what we'll be having is the range will be given by the u parallel into t. So here t represents the time of flight, plus half a parallel into t square. Now when we substitute the value of this a parallel, that is what will be minus g sin alpha, and u parallel will be u cos theta. So putting the values u cos theta into t minus half g sin alpha into t square. On substituting the value of t, so t already is the time of flight, we have the result, which is 2u sin theta by g cos alpha. So what we have is we have an expression like this, and here we can see we will be able to take some terms common out, and on taking the terms common out, so we can see what are the terms that will be coming out common. So here we'll have u square, which can be taken out common, and then we have by g into cos alpha, that also will be coming out common, u square by g into cos alpha. The remaining things, of course 1 2 also will be taken out. The remaining things will be sin theta cos theta minus sin alpha sin square theta by cos alpha. So we can see probably we will be able to take one more term common out, which is sin theta. So what we'll have is 2u square sin theta by g into cos square alpha. We'll take an LCM of this. So what we'll have is inside the bracket cos theta into cos alpha minus sin theta into sin alpha. So if you look at this, we have an trigonometric property, which is cos A cos B minus sin A sin B. The value will be equal to cos of A plus B. So by using that result, the final answer that we will be having is 2u square by g sin theta divided by cos square alpha into cos of theta plus alpha. So here we are using a trigonometric property, that is cos theta into cos alpha minus sin theta into sin alpha will be equal to cos of theta plus alpha. So this is the result for the range, which is the distance covered by the projectile along the inclined plane. So this is how we'll go about studying the projectile along an inclined plane.